Thanks for inviting me here, and also thanks for joining this session. I have to start with one disclaimer. The CRaC that I will be talking about. Okay, good. The CRaC that I will be talking about is coordinated restore at checkpoint. I've done some talks about this subject already, and my colleagues too. And if we're talking about distributions with CRaC and using CRaC, we are not talking about the medicine, let's call it, but we're talking about a system within Java. Okay, and it's all about this curve, which is an important curve, and I will explain further in this session, is the warm-up and getting to the optimal speed of a Java application. And I will explain how we can reach this and why it's so important. And with CRaC, we can achieve a very fast startup. And that's, of course, the main topic of this talk. So we'll also come back to this. But as I will explain this subject, I also need to refer a few times to the OpenJDK project itself and what I learned and found of what is happening in that project and what you can learn from the sources of the Java and OpenJDK project. Now, to make it easy for you to understand my story and why I'm telling this story exactly this way is I want to share some history about myself. I started programming in the 80s, and this was my very first computer. And what I found so important and so wonderful about this machine is that I could interact with the physical world. I could control electronic components like a relay board, so I could control my Lego trains, and along the tracks of my Lego trains there was some magnetic switches, so my computer could even know where the train was. So through the joystick ports of my Commodore 64, I knew where the train was. I could control it. I could stop it. I could start it. So at that time, I got fascinated by how software can control physical things and interact with the physical world. Now, my interest in computers and media led me to film school. And from that film school on, I went through a whole cycle of video editing, then multimedia. It was the start of the move from analog to digital video. It was also the rise of internet and the very first websites, and then YouTube didn't even exist. So I had to find my way into all this kind of different technologies. And it's only the last part of my career, the last 10, 15 years, that I joined the open source world, and I discovered Java and JavaFX as being those tools that are free to use, available for everyone, and provide very good tools, developer experience, and are evolving very fast now. So I went through this whole journey and I became a Java developer, but I didn't really knew what was happening in that system, how Java became Java, and how new features get introduced. And those are the things I learned only recently. Now, 4 years ago, I wanted to try something different. I was a Java developer. I had already done a lot of Java development, and I wanted to try something new with that knowledge. And that's when I started this project for my son, and I was using a Raspberry Pi, a touchscreen, an Arduino, to again control physical things. The same experiments I was doing over 30 years ago as a teenager, actually almost 40 years ago. And I wanted to control these lights and find out how I could use Java to do this on a Raspberry Pi, control LED strips. And I found out that I could use all the same tools that I use in my daily job, like, for instance, an API to let our son know that dinner is on the table and he has to stop drumming. So all these tools that I knew as a Java developer, I could suddenly use also on a Raspberry Pi and control physical things. But it was a rather difficult journey. Like, for instance, blinking this LED took me several days to reach that stage. I had to find out step by step how I could do that on a Raspberry Pi, how I could use Java on an embedded platform. I used this test setup for almost 6 months to each time replace the component on the breadboard you see at the bottom of this picture, and find out how I could control it, what type of commands I need, what kind of communication I needed. And I wrote it down. Everything ended up in a book. And during that journey, I learned how to use Java on Raspberry Pi. I described everything. I became a writer next to my job as being a developer. It's also how I joined the Pi4J project. I invite everyone who's interested specifically in this topic of using Java on Raspberry Pi to control physical things. This is the website you should visit. But since that day, I'm a bit known as the Java on Raspberry Pi guy. I'm the one who's experimenting with Java on Raspberry Pi, and that's how CRaC also became a topic I have been experimenting with. Now, over 1.5 years ago, I joined Azul, one of the Java distributors, and it's a company focused on Java and only Java. We make runtimes, we make distributions like Zulu and Prime, but we also make additional tools on top of those runtimes, like, for instance, Azul vulnerability detection. We recently published the state of Java, how Java is being used in companies, which versions, which distributions. So if you're interested in this topic, visit the azul.com website and you can download this report for free. So to summarize that history, I am a Java developer. I have done a lot of Java development, but by joining Azul, I became part of the team who is creating Java. I'm in the docs team, so me and my colleague write all the docs for Azul. But actually, the people who work at Azul are the people who are part of that big community who develop Java and OpenJDK. And that's also how I got insights into how the OpenJDK project is managed, how it grows, how new features are added. And I will share a bit of the knowledge that I gained recently in that project. As a side effect of that, I even became a Java champion. I'm still very honored that I'm amongst that small group of people who like to talk about Java, about how Java is evolving, and what you can learn from all these evolutions and how you can use it. So some things I learned while working with Java recently is, if you don't know SDKman yet, please go to the website sdkman.io. Download this tool if you're on Mac or Linux. You can also use it on Windows. I didn't try it myself, but it should work. And it will allow you to experiment with different versions of Java and very easily switch between Java versions. You'll see a few screenshots in my presentation that are made with SDKman. There's one important difference that we need to understand here and that I need to explain is the difference between Java and OpenJDK. So actually Java is a trademark. It's a name. It's the name of the programming language, and it also defines the Java technology compatibility kit. How can you know that a Java runtime, a JVM, a JDK, is compatible and will execute Java as it should be? And that's the TCK. So if a distribution has been tested and is compliant with TCK, you can be sure that it will execute your Java code as expected. And there are many distributions, we will come back to that. So that's one important thing to keep in mind. A Java runtime should be TCK tested. Now, what is OpenJDK? OpenJDK is actually the reference implementation of the Java platform, and it's an open source project. So you can find it on GitHub. It's free to use and modify. So everyone can find the sources of the OpenJDK runtime and the Java language in there. And it's a programming language, but it's also the JVM and the core libraries. So if you go to github.com/OpenJDK and then go to the JDK repository, that's where you will find the sources of the Java that we are running on our machines. There are many repositories there, 110 you see in the screenshot. There's also one, for instance, for CRaC. So CRaC is a project within OpenJDK where CRaC is being developed. CRaC is not a part of JDK yet, but it's a project which is developed there. So everyone, again, can test it, can contribute it, can use it, and experiment with it. Now, because the JDK, all the sources are on GitHub, you can also get them from GitHub and try them out yourself. I have a post on my blog, webtechie.be, where I tried to build the OpenJDK runtime myself on a Raspberry Pi. And actually, it's very easy. You just follow the README. You have to install various extra tools that you can do simply by sudo apt install. And it allows you to build the latest version of OpenJDK, which is in the sources. And I redid this a few weeks ago, and I did it from the CRaC repository. And it took me, I think, 1.5 hours to build that runtime. And then if you run the Java version command, which is actually executing the Java runtime and asking it for its version, then you see that instead of the pre-installed 21 that I was using before, which is just the Java version that the system recognizes, but when I run this specific Java version that I built from the CRaC sources, then it says I'm running 22 internal. Yes, indeed, you can already run Java 22, which is not finished yet, but which is ongoing project in development. If you just download the sources, you can build 22 and run your application with 22, the pre-release or your own built version of it. And that brings us a bit to the topic of versions and releases. Most of us know the whole evolution. We went through all these versions, and we have the long-term support version. So these are the versions that the distributors promise and have a timeline that they will keep them up to date and secure for many more years. So we had 21 recently. But what a lot of people are not aware of is that every 3 months, there is a new build, a new release of OpenJDK by various distributors with updates, security updates, bug fixes, sometimes even a backport of a new feature from a higher version. So there's a difference between upgrading and updating. Upgrading is really moving through the major versions, and most companies stick to the long-term support versions. But there's another important thing, and that's updating, keeping your Java runtime up to date. And why is it important? Let's check it. So I cannot do a poll very easily here, but if you're on version 17, do you know on which version of 17 you are? Huh? If you look, for instance, with SDKman, at all the versions that are available of Java for, in this case, macOS, and I just ask for version 17 of Azul Zulu, then you can see that we are actually on 1709. So there are already 9 builds, updates of Java 17, the major version 17. And each new version there includes security fixes and bug fixes. Now, let's go to the release notes, and that's actually where I live, and that's my current job, is keeping these release notes up to date and writing them. So if you look at the October release notes, then we can scroll through the CVEs. So these are actually vulnerabilities which got fixed in that version of Java 17. Let's move on to the table. So here we are at 1708 and 1709. So these were the OpenJDK versions that got fixed, and includes 3 CVEs, in this case in Azul Zulu. If you go back to July of last summer, the list is even longer. So keeping your system up to date will ensure that certain security issues that were discovered in the previous months are fixed, and without changing anything in your application code itself, just by changing the runtime, you profit from all these changes, and you will be sure to have a secure version again. So updating your runtime is very important. It will also bring some improvements and even maybe new features. Come back to that also later. But also, do you also know which distribution of Java that you're using? Again, to SDKman. Now, let's just list all the versions of 1709 which are available. And you see that there are really many distributions available. Amazon has one, we have the Graal, we have Liberica, Oracle, Microsoft, Submachine, Temurin, a lot. So all these versions are available, and they are all built of OpenJDK. So they come from the same sources, but they can be different. And like, for instance, for Zulu, there are versions available which include CRaC, not on macOS, but on Linux. So choosing a distribution can have an impact on what functionality is available, and even performance can be different between these distributions. The whole story about updates, upgrades, distributions, support contracts, licensing information has been described by my colleague Simon Ritter, the CTO of Azul, in a book, OpenJDK Migration for Dummies. Yes, it's written by someone from Azul, but the biggest part of the book is vendor neutral. So it gives you a lot of insights about this story, about different distributions and how you can use them, and what is important to know if you pick a certain distribution. Again, this book is for free. Just go to the azul.com website and you can find a link there and download the ebook. Now, another thing I want to show you is it's not only security fixes which are in these update versions of the OpenJDK builds, but there are some other things changing there. And one nice discovery in one of these release notes is the time zone and currency database. If you use JShell, which is, by the way, a very great tool to test Java code or to explain something in Java to anyone. For instance, here the zone ID, which is one of the classes in the Java time package. If you ask for the available zones, you will find 603 time zones. These are only a few of them. So all these time zones are defined within the OpenJDK project. And it's like reading a history book. If you go to the GitHub project of OpenJDK and you go to JDK, you will find a TZ data directory where you can read the history about all this data. And it's really reading a history book. It's for me, this was a discovery, finding all this information here, and it's in a readable format. There's really, why was it decided to remove daylight savings or don't have daylight saving in a certain period? Hopefully we will even get rid of these daylight savings soon, as they will be removed and no longer used. I hope so. But this is the kind of data you can find in the OpenJDK project. And why is it important is it's not only time zones, it's also location data and data related to countries. If you, for instance, look at the release notes of January of this year, we see that the IANA time zone database version 2022G was used. And why is this important? So the IANA database is managed on the IANA website, and it's a global project to handle all this kind of data, and changes of the IANA database are ported to OpenJDK. And here we find back this 2022G version. And it's not only time zone data, it's also data related to currencies and countries. If you look at 2 November of 2022, apparently Croatia had a currency change. And by changing the OpenJDK version, we have some very strange effects. So testing with 1901, if we ask for the currency in Croatia, which is HR as the code, we get the Croatian kuna. This is the currency in Croatia according to OpenJDK 1901. Now, if we move to 1902, And with the exact same code, we suddenly get the euro because Croatia joined the euro region. So if you have a unit test or some other integration test and you're testing currencies for a specific country, updating your runtime can have an effect. But on the other hand, it also makes sure that your application behaves like it should be, because currency codes and daylight savings and stuff like that is included in the OpenJDK runtime. So by using the latest one, you're not only sure about security fixtures which got added, but also that data like this is updated. And getting out of JShell, if you have the problem of exiting Vim, the same problem can happen in JShell, it's just /exit. But there are other changes between runtimes, like for instance, Zulu 17 and Zulu 21, which are also OpenJDK builds, and the ones for Linux, they are also available with CRaC. So with the still ongoing development of CRaC is included in these builds if you download the right versions. So not all distributions of Java are the same. Some can have additional components added, like some have JavaFX included, or some have CRaC included, like we provide on the Azul website. And CRaC is all about Warmup. And what is Warmup? To come to that story, we have to first go back to the basics, and that's bytecode. So we write Java code. As developers, we write Java code. Like hello world.java is a class which does something. It outputs hello world. Now, before we execute that code, it goes through the compiler, javac, and the compiler makes bytecode from our Java code. So it becomes a class file. And the class file, the intention of the class file is to be executable on all platforms. So the Java runtime installed on a Linux machine can run this on a Mac, on a Windows, on an Intel processor, on an ARM processor. They can all execute this bytecode and produce the expected result. But the bytecode is meant to be generic for all platforms. It's not optimized yet for the platform where it's running on. So what do we see if we start an application like this? And here we have to look at the yellow part at the beginning of the application. So the application starts, it loads the class files, it executes the code. It's not optimized for the system it's running on, but it can behave like it should. It will produce the output that we expect, but not very fast. It's not optimized yet. But Java, the runtime, will count how many times this code has been used or executed. And as soon as a certain threshold is reached, it will try to optimize this code, make native code out of it as fast as possible, so that it can replace the generic bytecode to platform-specific native code. And that's the green block. So we see that our application starts running faster. It can process more data. It's doing its work more efficiently. But again, the runtime will count how many times the code is used, but also how it's used. If you, for instance, have a switch case with 5 cases, and a few of them are never used, then in the native code that's produced, these 2 cases will just be removed and an error handler is added. And it will start using this more optimized, better native code, which was longer to compile, but performs better. And that's when the blue area appears. And then you see again some drops. And these drops appear when some of the assumptions were not correct. Like, for instance, I said some of these cases are never used, so they're thrown out and an error handler is added. But at some point, the 4th case is needed. Then it will go back to the bytecode, recompile it again with the 4th case included. And then you have, again, the right code executing more performant. And at some level, you reach the maximum performance of your application for that specific machine, that platform. You still see some drops. Those could be from the garbage collector. So each Java application which starts up goes through this process. And that's important to understand. If you have an application which is architected to scale, that you have 2, 3 more instances of the same application, then each of these instances has to go through this warm-up phase. They all have to learn how the code is used and how it should be optimized and compiled to native code. So it will take some time before each new instance, or if you restart application, will reach its maximum performance. So you have this cycle happening every time you start an application. So it starts with interpretation of the compiled code. It will profile and find the hotspots. These hotspots and this code which is used the most is compiled very fast, but low optimized to perform better. Again, it will be profiled to find also the hot code, which code is actually used and how it's used. And it will compile it again, which takes more time, but it's highly optimized, and it will perform at the maximum that it can do. And if a wrong assumption was taken, it will de-optimize and you will have the cycle again. But that doesn't happen a lot, but it does happen. So what could be a solution to prevent this cycle happening all the time at each startup of your application? Now, then we can go to ahead of time. Instead of just-in-time compilation, we have ahead of time. So we do everything up front. If we build our application in our build pipeline, for instance, we will produce native code directly for Windows, for Mac, for Linux, for each type processor, and we'll use those executables on a platform. So no interpretation of bytecodes, no analysis. So we lose all that, and we can start right immediately at full performance. But actually, and GraalVM is doing this, but actually what we see is if people use this approach, and that's a discussion and conversation I had at a lot of conferences lately, is that people are not happy with the performance of their native compiled, ahead of time compiled application. And why is that? And that's actually because you lose a lot of the advantages of the JIT compiler. Because the JIT can always return to that bytecode, it can always re-optimize the code to match the exact use case of the day. Again, those 5 cases. Today you only need 4, but maybe tomorrow you need 5, and the day after you only use 2 of these cases. The JIT compiler is able to further optimize your code and go back to the byte code and recompile it again. And that's something which is not possible anymore with ahead of time compilation. So there is a trade-off here. Again, it's software. It depends what is the right use case. But we see that JIT wins in a lot of cases if you compare it to ahead of time. So we need to find a solution. Now we can start always from that warmed up state so that we can skip the whole interpretation and the first compilation, that we immediately go to the perfectly optimized code. Now with Prime, at Azul, we have a lot of experience in this topic. So we have a solution which is built into Azul Prime, which is a licensed model, is a licensed runtime based on OpenJDK, but with some other tools in it. And Ready Now is one of those tools that we include in that runtime. And there you see that we can immediately go to maximum performance. But there's a problem here. Azul Prime is primarily aiming at high-end applications on servers, cloud stuff. So we needed a solution which was also usable for a whole lot of use cases. And people are not aware of this, but as Java was originally created to run on set-top boxes, for instance, to control your television. So it was very lightweight and still used in a lot of these use cases like infotainment systems, navigation, IoT gateways, running on embedded platforms. Like, for instance, a lot of cars have multiple Java systems. They have a system of a lot of different computers from different suppliers, and some of these run on Java. So you want your car and your navigation to start as fast as possible if you start your car. And that's where our clients needed a solution. And that's why we came up eventually with CRaC. So what is the idea of CRaC? And every word here is important. So the checkpoint. So from a running application, a checkpoint can be created. We can take a checkpoint from an application. So it was warmed up and we stop it at some point and we store that state of the application. That's the checkpoint. Now restore is that we can, from the checkpoint, restart the application as a restore. So the moment we stop the application is also where we restart the application. So it will just continue its work like we stopped it. And then the coordinated is something additionally, which we really needed to add to the OpenJDK. And that is an API that you can inform your application that a checkpoint will be created and a restore has happened. And why is this important? For instance, you don't want to keep your database connections open. If you stop your application, then your database connection is gone, and it doesn't make sense to keep it open somewhere. So you can tell your application, close the connection to the database because we're going to create a checkpoint. We cannot have this file open. Also for files, log files, socket connections, stuff like that, they can be closed before a checkpoint is created. And they should, by the way. And then after the restore, you need to inform, or your application needs to be informed that it needs to reopen these database connections or the file connections and stuff like that. So that's the coordinated part of this CRaC system. So we announced the availability of Zulu with CRaC in May of this year. We were, of course, already working on it for quite some time. And with that initial announcement, we also had this table where we experimented with different frameworks. And for instance, the Spring Boot project, we went from 4-second startup to 38 milliseconds. And you have similar results for the other frameworks. Now, all these frameworks, at that time, we needed to have some hacks in them to enable this CRaC system, but now they are all providing a version where CRaC is already integrated. Now, how do you add CRaC to an existing project? There is a dependency that you can add that provides the API. And there are actually two methods to be overridden wherever you need to open or close a connection. And that's the before checkpoint and after restore. But I will show you in a moment some code here. Now, because we announced this, and I am the Java and Raspberry Pi guy, I immediately got the question, can I also do this on Raspberry Pi? Does this run on a Raspberry Pi? And I immediately started experimenting with it. So this is a post of June this year. I tried to run CRaC runtime and stop an application and restart it again. But at that time, it didn't work for a few reasons. But the most important reason is, and this actually reveals a bit of how CRaC is working. CRaC at this moment for Linux is using Creo. And Creo is a checkpoint restore support system in Linux, which needs to be enabled. And for Raspberry Pi itself, for the operating system they provide and the Linux kernel that they are using, this option was not selected. So I proposed a change in the GitHub project where this Linux kernel lives. I had the luck that it was accepted because it's really only a configuration change. There's no real impact on the size of the kernel. And we can see that this was actually added at some point in a commit. And it's just a setting which is now enabled as yes. And it's fun to see that on October the 4th, so last month, a stable tag was added to this project. And it's a major change because there are over 100,000 additions to the Linux kernel for the Raspberry Pi. And we see indeed that this checkpoint restore is included in that tag. Now, why is it that Raspberry Pi is working on a new kernel release? Everything is linked to the release of the Raspberry Pi 5, which is a new board that they announced in September. It became available in October, and the deliveries started this month. And they have a new Linux Raspberry Pi operating system for this board. By the way, I received one, but because of these conferences and other conferences and a lot of work, it's still in the box waiting to be tested. But that Raspberry Pi operating system is based on Debian Bookworm, so that's the latest version of Debian. And you see the stack, which is indeed in the beginning of October. So I retested CRaC on Raspberry Pi, and without any change required, you can now run cracked applications on the Raspberry Pi operating system. So again, on my blog, webtechie.be, you can find articles about this. Now, I have a little demo application. I'm looking at the time. And this application uses Jetty. It's actually an example of the CRaC project itself, which I extended with a PostgreSQL database and some CSV files. So you can find it on github.com, my account CRaC example. And the idea of this project is to load data from a zip file. So it has to unzip this file. It's CSV, so every line is a record, and each record gets added to a list. So the first time you request a certain file, it takes some time because it has to unzip this file, store it in memory as all Java objects, and then you can request it from an HTTP call. So this is what's happening, let's see, in the CSV manager. So here, a list is stored with the data sets. They can be loaded from these files. And if data needs to be loaded, it will get it from the zip file. So it's just a demo application which takes some time the first time you call it. That was the idea, to show that the next time you call one of these functions, it will respond a lot faster. Now, the database manager is there to store the logs so that you see which file were requested, how many times, and you have some logs about the duration of the execution of each method. So here we see that the database manager is added to the core, which is part of the CRaC API. So we add this object, this class, to the context so that it knows which classes it needs to call when creating a checkpoint and when restoring. And here we have these overrides. And that you see before the checkpoint, it will close the connection. And after the restore, so when the application has restarted, it will end the connection again. And the same is happening with the Jetty server. Here we again have this register and the before and after restore. So we make sure that our application will be correctly close all open connections when we want to exit the application. So let's see how this works. We can then start the application with an extra argument command line option to tell it where to store the checkpoint. And once the application is running from a second terminal, we can instruct it to create a checkpoint. And when that's done and created the checkpoint, we can execute it and restart it again from that checkpoint. So we don't need the jar command anymore here of the jar argument. We just restore it from the checkpoint. Okay. So let's see how this works on a Raspberry Pi. You see that the checkpoint directory is still empty. In the first terminal, I'm starting the application. Starting the application from the jar file takes 5 seconds the first time. So this is starting the application from the jar. And from that time on, we have everything available in the browser and we can request the different files. Now, unzipping a small file with 1,000 records goes pretty fast. The same for 10,000 records. So here we are within 400 and 700 milliseconds. So let's skip a bit further and go to the big file. And now we are requesting the file of 1 million records, and we see that it has taken 16 seconds. But now all the files are in memory. Now, if we request the same file again and the first 100 records of the big one, we get a result in 8 milliseconds. So that means that our whole application has warmed up. Every method has been called. And everything is stored in memory. Everything that we want to have in memory is already loaded and is available there. Now we can create the checkpoint. So that's in the second terminal that the checkpoint command is triggered through J command. And you will see that it will, in the output, show that the checkpoint process is ongoing. And in this directory, all the files are created that are part of the checkpoint. And this goes on for a few seconds. And at the end, you will see in the first terminal that the application is killed. So creating a checkpoint is also killing your application. So if the checkpoint was successfully created, your application is killed, it stops. That's where the checkpoint process ends. So we'll see here, it's killed, the checkpoint is ready. Now, if we go to the next video, we can restart from this checkpoint you see here. And within a second, it's too fast to even have a clue how fast it goes. Our application is available again. And if we now request the 1 million file again and the first 100 records, we have immediately the same response time we had before, only 6 milliseconds. So if you do this a few times more, it's 4 milliseconds, 15, 5. So depending on the speed of the performance of the board at that time. So this is running on a Raspberry Pi. So this is the Java code that we use daily in our jobs, is running on a Raspberry Pi, can be executed on a Raspberry Pi, and it's ideal for testing this kind of things. You don't need an expensive cloud server to do these kinds of tests and experiment with these new technologies. Okay, let's move on a bit. The current state of CRaC is that it's an OpenJDK project, so you can find it on openjdk.org/projects. There you have CRaC. And we hope to have some JEPs soon. That means that a JEP can bring it to the OpenJDK project so that it can become part of OpenJDK, the distributions that you get from all the different distributors. There is also Project Lion, which is a bit similar, but that will take some more time before it becomes available. Now, how can you use CRaC? Go to docs.azul.com. In the core section, there you can find a lot of information about CRaC. CRaC is already available in AWS Lambda Snapstart, so that's based on CRaC. So if you upload a new Java Lambda to AWS, they will run it for you immediately in the background and actually store the snapshot, the checkpoint, and start from the checkpoint each time you execute a Lambda. And there are different projects which have support for CRaC, like Spring Boot, Quarkus, Micronaut. Also, all that is documented on GitHub. Okay, so you can also find a lot of this information on Fuji, the website for the Friends of OpenJDK, where you can find a lot of articles, at least one per day. Also, my content is there if you want to experiment with Java on the Raspberry Pi. And you can also find the Fuji podcast on there with each month a few episodes about all Java-related topics. And tomorrow, if you want to know more about Fuji, Geert-Jan Willinga, my colleague, and me will be talking about Fuji also here at JCon, I think at 12 CET tomorrow. Here at JCon. Okay, so I invite you to join me on Mastodon, LinkedIn, wherever you can find me. I write a lot about this on fuji.io and of course also on docs.azul.com. And I invite you to experiment, fail and learn a lot. For instance, on the Raspberry Pi, a very affordable device where you can experiment with this kind of new technologies. That's it.